Good day, stats students. So today we're going to go over both sections 2.6 and 2.7. 2.6 will be very quick. 2.7 will take some time. Might need to pause somewhere in the middle of 2.7 because it's going to be a little longer. Okay. So section 2.6. What to do about outliers? I get this question a lot, and so this is not an exhaustive list, but it gives you the main things to do about outliers. Okay. So the first thing is that when you get an outlier, the very first thing that you should do is check to see if there was a mistake made. Maybe there was some data entry that was incorrect, and maybe you could go back and correct that. Okay, or did the person who did the survey maybe misunderstand the question, or maybe the question wasn't worded properly. So you got to go back and check to make sure that everybody understood exactly what you were asking as far as the researcher's standpoint goes, and was there any mistakes made. Okay, so if a mistake was made, you can delete it if you can't update the number. All right, or you can go ahead and re-enter it. Obviously, if instead of maybe 27 was put in there, but 72 should have been put in there. It was transposed. Okay, go ahead and update it. All right. So outliers might tell you that there's some error in the data. Okay. What happens if the data is legitimate, though? Well, basically we got to keep it then. All right. Well, I shouldn't say that in every situation, but a lot of times we're going to be keeping it. And so it just belongs in the data set, and it's a natural source of variability, meaning the variability is going to go up because of that outlier, and that's natural for that variable, and you keep it, and it might be the most interesting thing about your data set. All right. However, there is a third possibility, and that maybe this person or thing that caused the outliers belongs in a different group. So I actually have a real life example with regards to this that happened to me. So I wasn't always a professor. I worked for, I was manager of forecasting analysis at a very large trucking company, another time in my life. Okay, and so when I was just kind of starting at the trucking company as an analyst, I pulled in some data, and I pulled in data for about 10 years worth of data, and everything lined up perfectly the way I expected it, except for three data points. And so I started asking around, and I go, what's up with these three values? And so one of the guys who was there for a lot longer said, oh, you know what you pulled in? You pulled in strike data. The union went on strike for 3 months, and you pulled in strike data. And so basically that data belonged to a different group. I'm not trying to I wasn't trying to analyze and forecast for basically where it was for both non-strike and strike months. That doesn't even make sense. Okay, so if I was going to forecast something for strike months, then I would look at those 3 months. But for all the rest of it that wasn't strike months, then that's what I wanted to pull in. And so there is a chance that you could actually get rid of the data, and this would be one of those chances where you kind of get rid of the data, because I wasn't trying to do anything with strike data. So I threw those out, and it made a lot more sense, the analysis at that point. Okay, so these are the three basic things that you can do when you have outliers, and that's really section 2.6. Okay. Oh, there's my example. All right, 2.7. All right, so we're going to get back into the variability of data. Okay, and so we already talked about the range and the IQR in a previous section. Okay, now we're going to talk about the variance, standard deviation. These are so important that the authors decided to give it its own section. Okay. All right, so here's our two data sets, data set A and data set B. Remember, we said data set B has larger variability than A. Okay, that should still certainly play out with the variance and standard deviation. So here's the formula for the variance. All right, and so we should break this up into pieces, parts. Okay, and some people get a little rattled when they start seeing formulas that have, 3, 4, 5 steps to them, and please don't. Okay, you've all been trained how to read a formula. Okay, it's just that maybe you haven't necessarily associated it with what you have learned in the past. So how do we read a formula? Believe it or not, you follow the order of operations. That is one of the basic things that why you learned the order of operations, believe it or not, was to actually read a formula. So let's review this for a second. Order of operations, right? You got your parentheses, right? And what do you do? Exponents, then multiplication, division, addition, subtraction, right? And so everybody pretty much has this memorized, okay? But why did we memorize it? Not to do a big string of numbers and figure out what do we got to do first or second. It's actually, believe it or not, to read a formula. Okay? It's one of the main reasons why. All right? So, if you keep this in mind, you can break down any formula into its basic parts and know what to do with it. Okay? All right. Now, before we get into reading the variance, there's one other thing that I want to bring up, and this is real obvious just about to everybody, but for maybe the 1 or 2 students that this might benefit, just be patient with me. All right? So I got a question for you guys. What's the difference between this statement? So we got 8 minus 2 divided by 6 minus 4. And this statement, 8 minus 2 divided by 6 minus 4. Notice they're both 8 minus 2 divided by 6 minus 4, right? But they're shown differently, aren't they? Well, there's a reason for this, right? So what's the difference? Well, in the first one, okay, you would have to do what first? Well, because there's no parentheses, there's no exponents, there's no multiplication, you would do the division first. You would do 2 divided by 6, and then you would start doing the subtractions. Okay? But what about the bottom one? Well, there's something inherently, there's something about that we're supposed to inherently know. Okay? And maybe it's maybe some math teachers haven't made this real obvious over the years, but when you have the division sign that goes straight across, okay, that's a line, like we do here, okay, what we have to think of is that, we have to do everything that's in the numerator and do everything that's in the denominator. Then what do we do in the end? We do the division sign. So it's like you're supposed to know that without even showing it, that there's actually parenthesis signs in both the numerator and the denominator. And so it's like you have to do the 8 minus 2 first, which is 6. You could do the 6 minus 4, which is 2, and you get 3. Okay? And so notice, let me take you back to the variance formula up there. Looks like we have that division sign there, doesn't it? Okay? So really what we have to think of is that we have to do everything in the numerator first, we have to do everything in the denominator, and then we're going to divide in the end. Okay, so we are still following the order of operations, just that we're supposed to know that there's basically parentheses in the numerator and in the denominator. Okay, so knowing that, it looks like we do have parentheses, right? And so what are we going to have to do first? We're going to have to do the x sub I. Now remember, since we have a little I there, doesn't mean that we just have one x, we have multiple x's, right? We have an x1, we have an x2, we have an x3, and an x4. It's all our values of our variable, right? Minus, and so for each one of those, what we're going to have to do, we're going to have to subtract off x bar. And what's x bar again? X bar is the sample mean, right? That's why it's so important to know those symbols. We got our sample mean. All right, so we're going to do that for each one of the x's. We're going to take x minus x bar for x sub 1, x sub 2, x sub 3. Do that, all right? And then what are we going to have to do? Well, do we have exponents? Yeah, we're squaring things. What are we squaring? Well, we're squaring all the x sub i's minus x bars. Okay, so we're going to have a multiple of those. We're going to have many of those. And what does the last step say? It says take all of those and sum. Remember, the summation signs tells us to sum something of the same thing. What's the same thing here? It's not the x's like it was in the mean. It's actually what? The x sub I minus x bar squared. Okay, so once we have all those and add them, we have our numerator. The denominator is pretty simple. It's n minus 1. It's our sample size minus 1. And then after we do that, we're going to divide, and there we go. Okay? So we're going to follow the order of operations. All right. So what are we going to have to do first? We're going to have to calculate x bar first. If that's not given to you in the problem, we're going to have to go ahead and calculate x bar. So I've done that already. It turns out to be 7. Okay. Now, if this happens when you do your homework, and if x bar happens to turn out to be 7.2, well, you're going to have to use 7.2. All right. I'm going to use a nice whole number here. Okay, so that it's real easy to calculate. Okay, but if it happens to be 7.2 or 8.6 or whatever, I'm going to have to leave it and work with a bunch of decimals. Okay. All right. Let's keep going here. So what I'm going to do here, what I found out the easiest way to do this, now you can do this in a long string of numbers if you wish, okay, but what I have found out is that if I put this in a column of numbers, okay, it works out so much better, okay, for students to understand. So I'm going to put little x, and so we got our data 1, 3, 5, 7, 9, 11, and 13, okay, so those are our x1, x2, x3, x4, okay, through x7, because we have 7 of those. Okay, and what's the very first thing that we have to do? We have to take each one of those and subtract off x bar. So I'm just going to make another column, call it xi minus x bar. And let's see, so we got 1 minus our 7, so 1 minus our x bar, we get a negative 6. Then we got 3 minus 7, we got a negative 4. We got a 5 minus 7, negative 2. 7 minus 7, 0. And so on and so forth. Okay, so you do this for each one of the x's. Okay, now here is a good place to kind of stop and make sure that you're doing everything correctly. Okay, if you've done everything correctly, this column always has to sum to 0. This column, this xi minus x bar, always has to sum to 0. Notice it does sum to 0 here. Okay, it's what we call the deviations. Okay, so if you anytime you calculate the deviations and add them up, it always sums to 0. Okay, all right, so we move on. Okay, we want to take all these values and do what with it? We want to square all of them, right? And so we're going to have another column, call it xi minus x bar squared. And so when we get to this column, we're not going to have any more negatives. Either we're going to have zeros or positive numbers. Okay, zeros or positive numbers. So we got negative 6 squared, we got 36. Negative 4 squared, 16. So on and so forth. Okay. All right. So we've done the hard part. Okay, believe it or not, that's all that was kind of the hard part. And if you think that was pretty easy, good. That's about as complicated as this is going to get. So once we add those up, okay, which turns out to be 112, I believe, that's going to be the numerator of the variance. Okay, that'll be the numerator of the variance. And the denominator, n, well, we had 7 observations. We had a sample size of 7. So 7 minus 1, that's 6. And so it turns out to be 18.6, and the 6 is repeating itself. Okay, so probably what I'm going to do, and probably what WebAssign will do, round to 2, maybe 2 decimal places. If it tells you round to 3 or 4, round properly, look at the next decimal, and if it's 5 or greater, round up. If it's 0 through 4, round down. So at some point we're going to have to round. Okay, and so I'm just going to round to 2 decimal places here. And so I'm going to say that the sample variance then is equal to 18.67, and remember our data was in terms of inches. Okay, and believe it or not, the units here for the variance is squared inches. It's whatever the units are squared. I don't know what the heck that means, but that's what it is. Okay, so technically the sample variance would be 18.67 squared inches. What does that mean? Well, The variance certainly has a big place in statistics. Okay, especially in upper statistics. Okay, and a lot of a little bit more complicated statistics, like if you were going to take graduate courses in stats. Okay, but in an introductory course like this, there's something a little more important than the variance. Okay, because somehow see, this makes a problem that we have squared units here, because it doesn't work nicely then with, say, the mean and all the other x's. Okay, but we'll address that problem here in a little bit. Okay, let's go ahead and calculate the variance for data set B. Okay, for data set B, there's our data. Okay, and I went ahead and calculated x bar. This time it turned out to be 13 for x bar. Okay, and so what am I going to do? I'm going to set up our column of numbers. Okay, I'm going to subtract off 13 for each one of those numbers. So we got 1 minus 13, negative 12, 5 minus 13, negative 8, so on and so forth. Okay, what should that sum to? That column not what it should, it has to. It has to sum to 0. If it does not sum to 0, you've done something wrong. Either you calculated x bar wrong, or one of your deviations was calculated wrong, or several of them were calculated incorrectly. Okay, so this has to sum to 0, this column. Clearly it does. So what's the next thing? We've got to take all those numbers and do what with them? Square them, right? And now we're going to get either zeros or positive numbers. So we got negative 12 squared, 144, negative 8 squared, 64, right? Negative 4 squared, 16, so on and so forth, right? We go ahead and add up those numbers. We get 448. That's our numerator, right? So our numerator is 448. This time I made the sample size 8. Okay, so that means our denominator is going to be 7, because it's n minus 1. And so this turns out to be a nice whole number, coincidentally. It turns out to be 64. So we would say that the sample variance for this data set turned out to be 64 squared inches, or inches squared, however you want to say that. Okay. All right. So let's we see that the variance has some potential problems in applied situations because of these squared units. Okay, so how are we going to take care of this? All right, well, that's where the standard deviation comes in. Okay, that's where the standard deviation comes in, and the standard deviation is just simply the square root of the variance. And so if you went back to the formula that I gave you before for the variance and just put a big old square root over the top of it, that's the standard deviation formula. Okay, that's the sample standard deviation. So going back to the standard deviation for A, I'm going to leave, when I calculated this, I went ahead and did this in Excel, and I left the 6 repeating so I can get a more accurate number for the standard deviation. So it turns out to be 4.32, and now take a look at the units here. It's inches. It's back to the units of x. That's important. Okay, that's important. So the units for the standard deviation is the units of x. So we can say that the standard deviation for A is 4.32 inches. For data set B, that square root of 64, right? That turns out to be 8. 8 what? 8 inches. Okay. All right. So now that we know how to calculate the standard deviation, let's talk about the standard deviation a little bit more, because there's a lot more to this. Okay, so first thing, standard deviation is the king of variability. Pretty much when people talk about variability or spread of the data, they're going to talk and refer to the standard deviation. All right, reasons: one, it uses all the values of the data set, just like the mean does. Okay, it looks at every value. Okay, not alone to calculate the sample mean, but to then calculate all those deviations. All right, and so that's an important thing. 2, it's more resistant more resistant to outliers than the range, not completely resistant. The IQER is a little bit more resistant, but it's more resistant than, say, the range is. Okay, so it's semi-resistant. All right. It has the same units as X. We already talked about that. That's an important thing. Now, let's talk about the definition of the standard deviation. This is important here. It is roughly the average distance the observations in the data set are from the mean. So it's roughly the average distance when looking at all the observations are from the mean. Okay. So here's a real simple data set. I got here's a dot plot that represents that data set. So I got one value at 2, one value at 4, one value at 6, 8, 10, and 12. Okay, so I want to go ahead and show you graphically what we're talking about when we're talking about the standard deviation. Okay, so I want to focus in on this definition. So the first thing is that we're going to need a mean, right? So the mean is located where? At 7. All right, in this particular data set. So 7 is the average, and this is what we're doing. Okay, when we calculate those deviations, what we're doing is we're saying, well, how far away is 6 from 7? Okay, in other words, we start with one of the observations and we go back to the mean. How far away is that distance? Then we go to the next one. How far away is the distance from 8 to 7? So on and so forth, from 4 to 7, to 10 to 7. Okay, and so we're basically figuring out those differences between those observations and the mean. Okay, so as you can imagine, for a data set that is more spread out than this, what's going to happen to these lines? The line's going to get larger. Okay, and so and thus the standard deviation is going to get larger the further away that they are from the mean. All right, so visually, that's what we're doing with the standard deviation. Okay, it's roughly the average distance that these observations are from the mean. Okay. Okay. Question for you: what would produce a standard deviation of 0? I want to think about it for a second. So what kind of data set would we need in order to produce a standard deviation of 0? Well, did you say something like this? If all the values in the data set are exactly what? The same. Like all of them were 6s, or all of them were 9s, or all of them were 13s. Okay, so if they were all exactly the same number, the mean would all be that number, and so all the deviations would be what? 0, and all the squared deviations would be 0. Okay, and so the numerator is going to be 0. Okay, and so our dot plot would look pretty boring. Okay, all the dots are exactly on the same spot. Okay, and there's no deviation. Okay, there's no deviation even in the graph because all the dots are sitting right there. Okay, at the same point. Otherwise, so as long as one of those dots is not exactly on 6 or exactly on 13, not exactly the same, even if it was 5.9, okay, you would start to have a standard deviation, okay, and it will be positive. There's no such thing as a negative standard deviation. There's no such thing as a negative variance. All right, there's no such thing as that. You can only have a standard deviation that is 0, and I just gave you that situation. Otherwise, it's going to be a positive number. Remember, we squared those deviations, got rid of all the negatives. Okay, so why did we do that? Why did we square the deviations? Well, the reason why we squared the deviations is because, remember, when we summed up the deviations themselves, it always turned out to be what? It always turned out to be 0. So we had these compensating negatives and positives. All right, and so we got to get rid of that. And so how did we get rid of them? By squaring them. Okay, and so we get rid of all the, we got rid of the negatives, we get rid of the positives. Well, we got rid of the negatives by turning them to positive, and the positive square is still a positive number, right? And there you go. Okay. So there's no such thing as a negative standard deviation. All right. let's talk, this is the last thing about the standard deviation as far as just generalities, then we're going to start to apply it. Okay, so population standard deviation, that's a parameter, right? It's a measurement coming from the population. It has a Greek letter, and it's the lowercase sigma. Okay, it's the Greek letter sigma, it's the lowercase sigma. Actually, the uppercase sigma is the summation sign that you've already been seeing. So there's what a sigma looks like. Okay, and the sample standard deviation, that's a statistic that's coming from a sample, a measurement from a sample. That's a stat. Okay, and the symbol that we're going to use is lowercase s. Lowercase s, larger a capital S. Okay, capital S is something else in statistics. So lowercase s. Let's see if the population standard deviation is sigma. That means the population variance must be what? Sigma squared. Sigma squared. And that means that the sample variance, the symbol for that is s squared. S squared. Okay? So we should have those symbols memorized ASAP. Okay? Because we're going to start seeing them throughout the textbook now. Okay? And throughout the lectures. Alright? Now note, I'm going to give you one final note, then we'll figure out how to apply this stuff. I gave you the formulas for the sample variance and sample standard deviation. Alright, the formulas for the corresponding parameters are slightly different, believe it or not. The problem is, it is not worth the explanation for this class to give you the difference and why that is. We would have to actually understand a little bit about theoretical statistics, and so there would be a huge explanation, several hours long, and some information with regards to a graduate level sort of class, and so we're not going to get into such things. Okay, but if you ever see a slightly different formula on, say, like the internet, you're working on the, you're working somehow on the internet, and you see a formula for the standard deviation or the variance, and it's just slightly different than what I just showed you here, it's probably because you're looking at the population. Okay, you're looking at the population standard deviation, you're looking at the population variance. Okay, so let's move on now. Alright, let's start to apply the standard deviation. Alright, so we have what's called the empirical rule, and this is only for bell-shaped data. Okay, so this is not for skewed left or skewed right, it's only for bell-shaped data. Alright, and there's 3 parts to it. And I'm going to break it down into each part. I'm going to show you a graph, okay, and hopefully by the time that I tell it to you in words and show it to you with the graph, it should be hopefully okay for you. Alright, part 1 says about 68% of the data is within one standard deviation of the mean. So the first thing is I use the word about. It's not exact, but it's pretty close. Okay, you're going to see where this comes from in another chapter. Alright, but for right now, we'll just say it's about 68%. Then the next thing I said, it's within one standard deviation. So within, does that mean less than? Does that mean greater than? Or does that mean in both directions from the mean? Well, that actually means what? Within means either direction, right? It doesn't matter if it's a little bit greater, a little bit less than. Okay, within one standard deviation. Okay. So, let me give you an example here. Let's say the heights of all U.S. Male adults are bell-shaped with a mean equaling 70 and a standard deviation of 4. So, basically, we're doing a little pretending here. The reason why is I said the heights of all U.S. males, right? And so I'm pretending that I have the data for the entire U.S. Male adult population. All right, which I told you, which is probably not going to be the case when a researcher does things. Okay, but we're in a little pretend time here. Okay, and let's say that we had all that data and we were able to calculate the mean, we were able to calculate the standard deviation. So that means mu is equal to 70, sigma is equal to 4. Now, could you also do this for sample data? Absolutely. It's just that instead of mu, it's going to change over to x bar, the sample mean, and instead of sigma, it's going to change over to s, the sample standard deviation. But we're going to assume that we have the population in front of us, okay? So we can do this problem. All right. So what I've done here, I've drawn a bell-shaped curve, okay? So let's see here. So remember I said the heights of all US males are bell-shaped. That's why I have a bell-shaped curve, okay? Now, where does the mean always go for bell-shaped data? The mean always goes smack dab right in the middle on the bottom, right? So 70, notice I put an X for this axis, and that's standing for US adult males in terms of inches. And I'm putting the mean, 70, smack dab right there in the middle. That's what we learned before. All right, and so what we're going to do is that we're going to go out one standard deviation in both directions from the mean. So we're going to go one standard deviation to the right and one standard deviation to the left of 70. Now what's a standard deviation worth here? Standard deviation was worth what? 4 units. It's not always worth 4, right? Another problem, it might be worth 30 or 100 or whatever. Okay, here it's worth 4. Okay, so we're going to go out 4 units to the right of 70. That would take us to what? 74. Then we're going to go out 4 units to the left of 70. What is that going to take us to? 66. All right. So if you go back to the original statement, it said about 68% of the data should be between those 2 points. So I highlighted it, and what we're saying is that the stuff in red, the stuff in the middle, okay, that's 66% of the data. It's about 2/3 of the, or excuse me, 68% of the data. It's about 2/3 of the data. Okay. So what we can say then is about 68% of the data is between what? 66 and 74 inches. In other words, about 68% of all U.S. adults have a height between what? 66 and 74. All right. So that's the first part of the empirical rule. All right, here's the second part. The second part says about 95% of the data is within 2 standard deviations of the mean. All right, well, let's go back to our graph. So right now we've only gone out 1 standard deviation from the mean. We got to go out 2 standard deviations from the mean, right? Both directions. So let's see, 74 is 1 standard deviation. We got to go out another standard deviation. We got to go out another 4 units. That would take us what? To 78. And then we at 66, that's 1 standard deviation to the left. We got to go out another standard deviation, right? That would take us to 62. We would draw lines right there. And the area shaded in red is about 95% of the data. So what that's telling us is that about 95% of all U.S. adults, males, all right, is going to have a height between what? 62 inches and 78. So that's the second part of the empirical rule. The third part says about, I know this doesn't sound like an about, it sounds very specific, but about 99.7% of the data is within 3 standard deviations of the mean. Let's go back to our graph. So here's our graph. So at 62 and 78, that's 2 standard deviations from the mean. We got to go out what? 1 more. Okay, so we go out 1 more. And from 78, we're going to add another 4 units. That'll take us to 82. From 62, we're going to go down to 58. We shade that in. Now, I want to make sure that you understand this. Stop for a second, okay? And notice the graph. Now, the graph looks very much completely shaded in, okay? However, I want you to realize this, is that the graph actually didn't stop. There is actually more data out to the right of 82, and there's more data out to the left of 58. Okay, very little data though. All right, very little data, but there is some data out there. All right, because remember what we said, that 99.7% of the data is between these 2 points. So there's still 0.3% still left. 0.15% to the right, 0.15% to the left of 58. All right. So what we can say is that we practically have all the data. All right. So what we can say is that about 99.7% of all U.S. male adults will have a height between what, 58 inches and 82. There you go. Empirical rule. So now, before we leave this, so what kind of questions could we give you on this one? Okay, so this slide just kind of reminded me of that. So let's go back to this slide right here. So there's two different types of questions that we can give you. We're going to give you I'll give you the standard deviation, the mean. I'll tell you it's bell-shaped. Okay, and hopefully you understand that. Oh, okay, I can apply the empirical rule. All right. So I might ask you, give me the interval of data where the middle 68% of the data lies. And you would say, okay, middle 68%, empirical rule, one standard deviation, so I got to go out one standard deviation from the mean. Oh, that would be from 66 to 74. Hopefully that makes sense to you. Or I might change it around and say, what percentage of the data is between 62 and 78? You go, oh, 62 and 78. Okay, so we went out two standard deviations from the mean. That means about 95% of the data is there. Okay, and so hopefully that gives you the idea of the types of questions that I can give you with regards to the empirical rule. All right, so let's move on to the last topic, and that is in section 2.7 anyways, z-scores. This is a really important topic. Okay, this has another name to it called the standardized score. Okay, so z-score is the number of standard deviations an observation is from the mean. This is an important concept in stats. Okay, and you're going to see why later on in the semester. Okay, so it's a really good idea to know this definition. I'm not going to ask you exactly what the definition is, but I expect you to know what the definition is so you can apply that that definition with problems. Okay, so let's go back to our problem here. Okay, and notice right now I have an axis of x, which is in terms of inches. Okay, which is in terms of inches. Now, we're not used to doing this too often, maybe ever, but I'm going to do it. I'm going to create another axis. I'm going to call it the z-axis, meaning z-scores. All right, so anytime you see z in statistics, it's z-scores. Okay, so I'm going to create another axis called the z-scores. All right, and so let's focus in on the 74 right now. So my question to you is, how many standard deviations is 74 from 70? How far is 74, that particular observation, from the mean of 70? And you go, that's just one standard deviation, right? That means the z-score for 74 would simply be 1. How about 78? How many standard deviations is 78 from 70, the mean? You would say, oh, that's 2 standard deviations. And 82, you would say 3 standard deviations. Okay? Well, we can go the opposite direction. Now be careful with this one. How about 66? 66 is one standard deviation away, but it's in the negative direction. Okay, it's in the negative direction. So 66 would be a z-score of a -1. 62 would be a z-score of -2, and 58 a -3. And what would be the z-score for 70? Well, we're 0 standard deviations from the mean, and so 70 would have a z-score of 0. Okay, so z-scores. So one thing that I want to point out to you right now is that you can have negative z-scores. Z-scores can be negative. And when would you have a z-score that's negative? You would have a z-score that's negative when the observation is what? Less than the mean. And you would have a positive z-score when the observation is what? Greater than the mean. Okay, that's all that a negative and positive z-scores mean. That you're either less than the mean or the observation is greater than the mean. Okay, what about the values that don't fall exactly at 1, 2, 3 standard deviations from the mean? Meaning, kind of that plays into the empirical rule. Can we calculate the z-scores for those values? Well, yeah. If I ask you the question, then probably the answer is yes, right? Silly question. Okay, so yes, we can, and it's a simple little formula. So, no matter how complicated the problem is, if you are standardizing something, it will follow this basic idea. All right. So a z-score is equal to the observed value, so the observation minus the mean of the data set that it's coming from, and then divide by the standard deviation. So since we got the line going straight across there, that means we have parentheses in the numerator. Okay. And we're going to divide completely, we're going to divide in the end. All right. So let's say that we go ahead and calculate the z-score for a U.S. adult male with a height of 63 inches. Okay, let's go ahead and do that. So that means our observed value is what? 63. What's the mean from which that observation is coming from? The mean for that data set, it would be 70. The standard deviation would be 4. So we have 63 minus 70 divided by 4. Now, that turns out to be a negative 1.75. Now, does that make sense? Does that make sense? Let's take a look at our graph. Okay, let's go back to our graph. Let's go back a couple of slides. Let's see 63. Let's see 63 is right here, and so let's see, that's between a negative 1 and a negative 2, right? And we fully expected that should have been between a negative 1 and a negative 2 for a z-score. So it makes perfect sense that we came up with a negative 1.75 for that z-score. All right, so we could do that for any height then. All right, we can do that for any height. Now, what I want to do next, and this is important, this is really important, okay, because students forget this as we go through the semester, is, well, what is the interpretation of z-scores? So let's go ahead and interpret this particular z-score. So we got a z-score of a negative 1.75. What exactly does that mean? Okay, you want to take your time with this one. So the male's height, so a male with a height of 63 inches, okay, so a male with a height of 63 inches, the male's height is what? 1.75. Now be careful, standard deviations. It's no longer in terms of x. That's kind of the point of z-scores. You've taken it out of the units of x, okay? You've taken it completely out of the units of x, okay? And we're looking at things in terms of standard deviations, all right? So the male's height is 1.75, what? Standard deviations, be careful, below. Now why below? Below because it was a negative 1.75. If this was a positive number, we wouldn't say below, we would say above, right? We talked about that already, all right? So the male's height being 63 inches is what? Is 1.75 standard deviations below the value of the mean. Okay, it's not in terms of inches, it's in terms of standard deviations. Okay? So let's not forget about this interpretation. All right? All right. Let's see here. So I want you to understand, this is an important... we're trying to hint towards a concept here in statistics that's really important, and most authors just don't even mention this, okay, even as we get into more complicated things. In statistics, we use the standard deviation as a unit of measurement. That's what we just did. We use the standard deviation as a unit of measurement. Notice the standard deviation is in the denominator, right? And notice in our interpretation, the male's height is what? 1.75 standard deviations. It's a unit of measurement now. Okay? That's important. That's actually one of the main jobs of the standard deviation, is to say how far is that thing from that thing in terms of the standard deviation. And this is our first example of it. All right, how far away is this from the mean? And that's what we call a z-score. But in terms of standard deviation, not in terms of the units of x. So this is a really important concept. Okay, is how does we use standard deviation? It's actually a unit of measurement for us. All right, One last thing, and then we'll end section 2.7, is that you can use z-scores to identify outliers. So there's more than one way to identify outliers. We saw one way that we would do that with box plots. We have another way, okay? We have another way using z-scores. It's real simple. If an observation has a z-score either less than a -3 or greater than a +3, it is an outlier. So once you start getting more than 3 standard deviations from the mean, there you go. Okay, the z-score method says that's an outlier. Okay, so if you got a z-score for an observation that's a -3.24, outlier. A positive 4.6, boy, you're getting to be an extreme outlier. Okay, you're really far out there. Okay, that observation anyways. All right, so that ends section 2.7, and I think this ends also chapter 2. Thank you for your time.